This section covers the concept of forces and Newton's laws of motion. And as you recall, what we have discussed so far is the concept of how we represent the state of a particle. We talk about a mass m, and that will be at the end of some vector r, which gives its position in a three-dimensional space. And as you know, that mass can move around, and so this position vector r can change with time. And this position vector r, as it changes with time, depends upon the three coordinates, x, y, and z, and therefore is a vector with these three components. We defined the velocity to be the change in that vector with respect to time. In calculus, we write it as dr dt, and that would be represented by dx dt, dy dt, and dz dt, for the velocity in the x, the y, and the z direction. And we discuss the acceleration, which is the change in the velocity. And it is the change in the velocity vector with respect to time, and therefore is the second derivative of x with respect to time, second derivative of y with respect to time, second derivative of z with respect to time. In other words, the change in the change. Or equivalently, it could be written as the change in this vector, in the velocity in the x direction, the y direction, and the z direction. And this gives us, of course, the acceleration in the x direction, acceleration in the y direction, acceleration in the z direction. Now, what you should be thinking about at this point is, okay, we have position, velocity, and acceleration. We have the concept of mass. We have the concept of a three-dimensional space in which things move around. Do we have to keep on taking the change and the change and the change and the change forever? Or is there some end to this and some way that we can think about this in a more collective way without knowing an infinite number of things? And the answer is yes. This brings us to the concept of a force. We intuitively know what a force is, and that it's a vector and has a direction. So if you put a force on something, like pushing a lawnmower, you notice that you're pushing it in a direction by a certain amount. And we know that mass is a resistance to that acceleration that it's going to experience. It's a measure of inertia. And so we're familiar already with mass measured in kilograms. And we know that if we take a mass like this one and put a force on it, it's going to change it. Change its velocity. If it's sitting still, it'll speed it up. If we have its velocity in a certain direction and we push a force in a perpendicular direction, it'll make that veer around like we do when we steer a car. And so forces cause acceleration. In an inertial frame of reference, if we have no force, it means that we have constant motion. That's our definition of what is called an inertial frame of reference. No force means no acceleration. Therefore, we have constant velocity. Well, the force is going to be our key to understanding how we prevent looking at the changes in acceleration, the changes in those, and the changes in those. Newton's first law, and there are three of these altogether, says that if the force is equal to 0, then this will imply that the acceleration is equal to 0. If there's no force, there's no acceleration. And conversely. In other words, either one of these implies the other. And both of these are vectors, so these are pretty strong statements. It applies, therefore, to the x, the y, and the z direction. If there's no force in the x direction, there's no acceleration in the x direction. No acceleration in the y direction, no force in the y direction, and so forth. And this is Newton's first law. Newton's first law is actually contained in Newton's second law. Newton's second law The second law states that the force is the mass times the acceleration. In other words, the force is proportional to the acceleration, and the constant of proportionality is given by the mass. Therefore, if something has twice the mass, it takes the same force will only give it half the acceleration, and so forth. So there's a total proportionality between the acceleration and the mass and the force. There's three variables. You'll notice that this second law actually contains the first, because if we have a zero acceleration, if this term is zero, it means that the force is zero, and this is a vector equation also. Likewise, if this is zero, this is zero. Why did Newton make a separate law? Because he wanted to emphasize to people that if something experiences no total force on it, then it'll continue in that motion in a straight line unless interrupted by some force. So the second law is given by this. And you'll notice that the units here are going to be kilograms, meters per second squared. And we have a new unit. Rather than call this a kilogram meter per second, rather than call it that all the time when we talk about a force, we give this the name of a Newton. So we say a Newton of force in honor of Sir Isaac Newton, who came up with this law, that if we have 1 kilogram mass accelerated a meter per second, then the force that it experiences is 1 Newton. And so a Newton of force will give us a kilogram, an acceleration of a meter per second squared. The exactly correct equation is a little bit different. This is an approximation, actually, for when the mass is constant. And although that other equation is not discussed until later, what I'm going to do is go on and introduce it now by defining the concept of momentum. We define momentum, p, as a vector, as the mass of a particle times its velocity. This is a definition for momentum. Momentum in physics is an incredibly important term, and the momentum is conserved in a system, both the linear momentum and the angular momentum, if there are no forces and no torques that are present on the whole system. Now, how does this momentum play a role with this? Well, if I look at this equation, this is actually mass times the derivative of the velocity with respect to time. Mass times derivative velocity with respect to time. Sorry, I'm kind of squeezing that there. Mass times change in velocity. It turns out that this is true only when the mass is constant, and that this derivative moves out front, so that what we can write is that the force is generally, and this is the exact equation, is equal to the derivative of momentum with respect to time. And the momentum is mv. Therefore, if the mass is constant, which is usually the case, then we can bring it out front of the derivative and get m dv dt, which then results in mass times acceleration. Now, when might that not be true? Well, that might not be true, for example, if you have a rocket. As the rocket moves along, just like a car moves along, it's using fuel out the back, so the rocket is weighing less and less. In fact, this is incredibly important with space travel, because you must lift off from the Earth with an enormous rocket load of fuel, and that fuel gets less and less and less as you move along. Likewise, a car which is moving along will weigh a little bit less due to the less gasoline that's in it. But another dominant example is a railroad car, and if we look at a railroad car on a track, often these cars are filled with coal or some other substance actually as they're moving. So as the car is moving, in particular as the train as a whole moves, the mass increases, or if it's dumping out the bottom, it can dump and therefore it would lose mass. So in certain cases, we do have a change in mass, and in those cases you have to be very careful to apply the exact equation, and I'm going to write here that this is exact. Now, what kind of simple problem might you expect for a situation like this? A simple problem might be a mass of 4 kilograms experiences an acceleration of 6 meters per second per second. What force was applied to it? Well, the force is the mass times the acceleration. So if we 4 times 6 would be 24 newtons. Likewise, anytime we have 2 of the 3 quantities, force, mass, and acceleration, we can solve for the other 2. Likewise, we could look for a change in momentum with respect to time. We might say, okay, we have a momentum P, which is equal to 6. Now, what are the units of momentum? The units of momentum are going to be kilogram meters per second. And that's the initial momentum. A momentum finally might be 30 kilogram meters per second. And it changes because of a force being applied to this system. It changes maybe in a time of delta t is equal to 2 seconds. So what would the total force be? The force would be the change in momentum, which would be 30 minus 6 divided by 2. And so that would be 24 divided by 2, which would be 12 newtons. And that would be the force that you would experience with that change in momentum over that change in time. Finally, there's one more Newton's law, and it's in a way kind of simple. It says that the force that particle 1 exerts on particle 2 is the negative of the force that particle 2 exerts upon particle 1. Now, originally, Newton erroneously stated that these forces were always along the lines of centers, meaning that if I had 2 particles, the forces were either directly towards each other or directly away from each other. And that is not true. We can have situations where the forces are equal and opposite, and they're kind of skew like this. And this is possible because Newton didn't know about all the different types of forces, such as spin forces that we have that we're aware of today. So in Newton's third law, when A pushes on B, B pushes back upon A with the same force that it has. So as 2 things push on each other, their total force vanishes, each pushing upon the other with the negative of the other one. Those are Newton's 3 laws, so you should be able to work a simple problem, especially with the second. Be familiar with the units. Understand how the first is a consequence of the second. And what the third law really means, as we'll find out more and more later on. So in the last section, we realized that we don't have to keep taking derivatives and derivatives. When we get to from the position to the velocity to the acceleration, we can stop there and make an equation between what happens with the acceleration and the force that is exerted on something. Well, now then, we have to say, what are the fundamental forces that we have in nature? Can we classify them? Is there a way to understand them? And yes, we do understand these forces, and it's one of the better understood things in all of physics. Forces, it turns out, as we'll show in quantum theory, arise from the exchange of virtual particles back and forth between 2 things. And there are 4 forces that arise from these exchanges of particles. The first of these is the most familiar force to everyone. It's the gravitational force. The gravitational force is given by the equation gravitation, given by the force gravity is equal to a universal constant, g, called the gravitational constant, times the mass of a first particle, mass of the second, divided by the distance between them squared. And it's always attractive. We know